Good morning, everyone. Today, I will discuss to you about chapter 7.2, finite difference. And with me is my better half, Engineer Uwais Piabunya, who will be discussing a simple implicit method and the front handle summation method. So I will discuss about the heat conduction equation and explicit methods. So, heat conduction equation. Uh, the heat conduction equation is conservation of heat can be used to develop a heat balance for the differential element in the long, thin, isolated rod shown in figure 1. However, rather than examine the steady state case, the present balance also considers the amount of heat stored in the element over a unit period, delta T. Thus, the balance is in the form inputs minus outputs equals to storage, or the function of x times delta y times delta z times delta t minus q x plus delta x times delta y times delta z times delta t is equals to, so the delta x times delta y times delta z rho times c times delta t. So this one is equal to inputs minus output is equal to the storage. So dividing by the volume of the element, delta x times delta y times delta z and delta t gives qx minus the quantity of q times x plus delta x over delta x is equal to rho sub rho c times delta t over delta small letter t. Taking the limit yields, so minus of q over derivative of q over x is equal to rho's times c times t over the t. Right? Dividing by the volume of the element, delta x times delta y times delta c and delta t gives the equation a times per second derivative of t with respect to x is equal to the derivative of t with respect to small letter t. This equation is the heat conduction equation. Just as with elliptic partial differential equations, parabolic equations can be solved by substituting finite divided differences for the partial derivatives, whereas elliptic equations were bounded in all relevant dimensions. Parabolic partial differential equations are temporarily open-ended. Because of their time variable nature, solutions of these equations involve a number of new issues, notably stability. These, as well as the other aspects of parabolic partial differential equations, will be examined in the following sections as we present two fundamental solution approaches, explicit and implicit schemes. So figure 2 shows a grid used for the finite difference solution of parabolic PDEs in two independent variables, such as the heat conduction equation. Note how, in contrast to figure 29, this grid is open-ended in the temporal dimension. Chapter topic number 2 is the explicit methods. Uh, Explicit methods. The heat conduction equation requires approximations for the second derivative in space and the first derivative in time. The former, the derivative in space, is represented in the same fashion as for the Laplace equation by a centered finite divided difference. So, the second derivative of t with respect to x is equal to uh, TL uh, sub I1 plus 2 minus 2 times 2L sub I plus 2 plus T L sub I minus 1 all over delta x squared. So which has an error of O times delta x squared. Notice the slight change in notation of the superscripts used to denote time. This is done so that a second subscript can be used to designate a second spatial dimension when the approach is expanded to two spatial dimensions. Forward finite divided difference is used to approximate the time derivative. So the first derivative of t is a capital letter T with respect to t is equal to t raised to n plus 1 sub I minus t raised to L sub I all over delta t, which has an error of O times delta t. So substituting uh, 7 point equation 7.2 and 7.2 into equation 1, equation 7.2.1 yields k times t raised to L sub I plus 1 minus 2 times t raised to L sub I plus t raised to L sub I minus 2 all over delta x squared is equal to t raised to L plus 1 sub I minus t raised to L sub I all over delta t, which is now our 7.2.4 equation. So, which can be solved for t raised to L plus 1 sub I is equal to t raised to L sub I plus uh, delta times are times lambda times the quantity of tel t raised to L sub I plus 1 minus 2 times t raised to L sub I plus 2 plus t raised to L sub I minus 1. And this will be now 7.2, equation 7.2.5, where lambda is equal to the constant k times delta t over uh, delta x squared. This equation can be written for all the entire nodes on the rod. It then provides an explicit means to compute values at each node for a future time based on the present values of the node and its neighbors. Notice that this approach is actually a manifestation of Euler's method for solving systems of ordinary differential equations. That is, if we know the temperature distribution as a function of position at an initial time, we can compute the distribution at a feature based on equation 7.2.5. A computational molecule for the explicit method is depicted, depicted in figure 3, showing the nodes that constitute the spatial and temporal approximations. These molecules can be contrasted with others in this chapter to illustrate the differences between the approaches. So, figure 3 below shows a computational molecule for the explicit form. So, where uh, x is equal to where x is the grid point involved in time differences, and the circle is the grid point involved in space difference. So, examples on explicit uh, solution of the one-dimensional heat conduction equation. So problem, use the explicit method to solve for the temperature distribution of a long thin rod with a length of 10 cm and the following value. K prime is equal to 0.49 cal per second cm degrees Celsius, and delta x is equal to 2 cm, and delta t is equal to 0.1 seconds at t is equal to 0. If the temperature of the rod is 0 and the boundary conditions are fixed for all times, at t equal to 0, then the temperature at 0 is equal to 100 degrees Celsius, and temperature at 10 is equal to 50 degrees Celsius. Note that the rod is aluminum with constant C is equal to 0.2174 cal per grams degrees Celsius, and the rule is equal to 2.7 gram per cubic centimeter. Therefore, K constant, that K is equal to 0.49 times divided by 2.7 times 0.2174 is equal to 0.835 centimeters squared per second, and lambda is equal to 0.835 times 0.1 divided by 2 squared. So lambda now is equal to 0.020875. Solution. Applying equation 7.2 gives the 0.2.5 gives the following value at time is equal to 0.1 second for the node at x equal to 2 centimeters. P raised to L sub 1 is equal to 0 plus 0.020875 times the quantity of 0 type minus 2 times 0 plus 100 is equal to 2.0875. At the interior points, our for x is equal to 4, 6, and 8 centimeters. The results are for t raised to 1 sub 2 is equal to 0. For t raised to 1 sub 3 is also equal to 0. And for t raised to 1 sub 4, we can get the 1.0438. At t is equal to 0.2 seconds, the value at the four interior nodes are computed as, so at t raised to 2 sub 1, so 2.0875 plus 0.20875 times the quantity of 0 minus 2 times 2 plus 2.0875 plus 100. So this will equate to 4.0878. And for t raised to 2 sub 2 is equal to 0 plus 0.020875 times the quantity of 0 minus 2 times 0 plus 2.0875 is equal to 0.043577. And for t raised to 2 sub 3 is equal to 0 plus 0.020875 times the sum of 1.0438 minus 2 times 0 plus 0. This will equate to 0.021782. And lastly, that t raised to 2 sub 4 is equal to 1.0438 plus 0.020875 times the sum of 50 minus 2 times 1.0438 times 0, and this will also equate to 2.0438. The computation is continued, and the result at 3-second intervals are depicted in figure 4 below. Captures the conduction of heat from the boundaries into bar. So figure 4, this is figure 4. This is the temperature distribution and a long thin rod as computed with the explicit method described in section C point, section 7.2.2. So you can see T is equal to 3, or time is equal to 3 seconds. So the temperature, or can get the temperature as this. At time is equal to 6 seconds, 9 seconds, and 12 seconds. So for delta T, or the increment in time is 0.1 seconds, and the increment in x is equal to 2. So, and the constant K is equal to 0.835. So for explicit methods, we have uh, convergence and stability. Convergence means that as the delta x and delta t, or the change in distance and change in time approach zero, the results of the finite difference technique approach the true solution. Stability means that errors at any stage of the computations are not amplified by, but are attenuated as the computation progresses. It can be shown that the explicit method is both convergent and stable if lambda is less than or equal to 1. Or, hmm, or delta t is less than or equal to 1/2 times delta x squared over k. This is our equation 7.2.6. In addition, it should be noted that setting lambda uh, less than or equal to 1/2 could result in a solution in which errors do not grow but oscillate. Setting lambda less than or equal to 1/4 ensures that the solution will not oscillate. It also known that setting lambda is equal to 1/6 tends to minimize the occasion error. This is from Carnahan et al. 1969. Figure 5 is an example of instability caused by violating equation 7.2.6. So this plot is for the same case as in example 7.1, but with lambda is equal to 0.735, which is considerably greater than 0.5, as in figure 5. The solution undergoes progressively increasing oscillations. This situation will continue to deteriorate as the computation continues. So this is figure 5. When we discuss it, we'll go back to this figure later. We'll first continue. So figure 5 is an example of instability caused by violating equation 7.2.6. This plot is for the same case as in example 1, but with lambda is equal to 0.735, which is considerably greater than 0.5 as in figure 5. The solution undergoes progressively increasing oscillations. This equation will continue to deteriorate as the computation continues. Although satisfaction of equation 7.2.6 will alleviate the instabilities of the sort manifested in figure 5, it also places a strong limitation on the explicit method. For example, suppose that delta x is half to improve the approximation of the spatial second derivative. According to equation 7.2.6, the time step must be quartered to maintain convergence and stability. Thus, to perform comparable computations, the time steps must be increased by a factor of 4. Furthermore, the computation for each of these time steps will take twice as long because halving of delta x doubles the total number of nodes for which equations must be written. Consequently, for the one-dimensional case, halving delta x results in an eightfold increase in the number of calculations. Thus, the computational burden may be large to attain acceptable accuracy, as will be described shortly. Other techniques are available that do not suffer from such severe limitations. As was the case for elliptic PDAs, derivative boundary conditions can be readily incorporated into parabolic equations. For a one-dimensional one, this necessitates adding two equations to characterize the heat balance at the end nodes. For example, the node at the left end, I equals to 0, would be represented by t raised to L plus 1 sub 0 is equal to t raised to L sub 0 plus the lambda times the sum of t raised to L sub 1 minus 2 times t raised to L sub 0 plus t raised to L sub negative 1. Thus, an imaginary point is introduced at I is equal to minus 1. However, as with the elliptic case, the point provides a vehicle for incorporating the derivative boundary condition into the analysis. Problem 2 at the end of the chapter deals with this exercise. So we will tackle it on example number 2. So this is um, this is the this is figure 5, which was previously mentioned. So you can see at every time difference, you can also see the difference in temperature with respect to like, so this illustration of instability is the solution for the result. Of example 1, lambda is equal to 0.735. So 7.2.2.3 or the higher order temporal approximations. The general idea of re-expressing the PDA as a system of ODEs is sometimes called the method of lines. Obviously, one way to improve on the Euler approach used above would be to employ a more accurate integration scheme for solving the ODEs. For example, the here method can be employed to obtain second-order temporal accuracy. An example of this approach is called McCormack's method. These and other improved explicit methods are discussed elsewhere. So, so these other methods are um, seen in other books. For example, you can see in this Hoffman 1954 books pertaining or discussing the finite difference or parabolic equations. So that will be the end of a report on 7.2 and 7.1 and 7.2. And now I will uh, give or turn over the discussion to Engineer Grace Yagonia.
Good day, everyone. I'll be reporting about the simple implicit method and the Crank-Nicholson method. The simple implicit method. As noted previously, explicit finite difference formulations have problems related to stability. In addition, as depicted in Figure 6, they exclude information that has a bearing on the solution. Implicit methods overcome both these difficulties at the expense of somewhat more complicated algorithms. In Figure 6, this is the representation of the effect of other nodes on the finite difference approximation at node IL using an explicit finite difference scheme. The shaded nodes have an influence on IL, whereas the unshaded nodes which in reality affect IL are excluded. The fundamental difference between explicit and implicit approximations is depicted in Figure 7. For the explicit method, we approximate the spatial derivative at time level L in Figure 7a. Recall that when we substituted this approximation into the partial differential equation, we obtained a difference equation 7.2.4 with a single unknown ti to the L plus 1. Thus, we can solve explicitly for this unknown as in equation 7.2.5. In implicit methods, the spatial derivative is approximated at an advanced time level L plus 1. For example, the second derivative would be approximated by Figure 7b. Second derivative of t with respect to x is approximately equal to ti plus 1 to the L plus 1 minus 2 times ti to the L plus 1 plus ti minus 1 to the L plus 1 over delta x squared. This is equation 7.2.7, which is second order accurate. When this relationship is substituted into the original PDE, the resulting difference equation contains several unknowns. Thus, it cannot be solved explicitly by simple algebraic rearrangement as was done in going from equation 7.2.4 to 7.2.5. Instead, the entire system of equations must be solved simultaneously. This is possible because, along with the boundary conditions, the implicit formulations result in a set of linear algebraic equations with the same number of unknowns. Thus, the method reduces to the solution of a set of simultaneous equations at each point in time. To illustrate how this is done, substitute equation 7.2.3 and 7.2.7 into equation 7.2.1 to give a k times ti plus 1 to the L plus 1 minus 2ti to the L plus 1 plus ti minus 1 to the L plus 1 over delta x squared equal to ti to the L plus 1 minus ti to the L over delta t, which can be expressed as negative lambda ti minus 1 to the L plus 1 plus 1 plus 2 lambda times ti to the L plus 1 minus lambda ti plus 1 to the L plus 1 equals ti to the L. This is equation 7.2.8, where lambda equals k times delta t over delta x squared. This equation applies to all but the first and the last interior nodes, which must be modified to reflect the boundary conditions. For the case where the temperature levels at the end of the rod are given, the boundary conditions at the left end of the rod, I equals 0, can be expressed as t 0 to the I plus 1 equals f of 0 to the times t to the L plus 1, where f of a function of 0 t to the L plus 1 equals a function describing how the boundary temperature changes with time. Substituting equation 7.2.9 into equation 7.2.8 gives the difference equation for the first interior node I equals 1. I plus 1 plus 2 to 2 times lambda times t1 to the L plus 1 minus lambda t2 to the L plus 1 is equal to t1 to the L plus lambda times function of 0 times t to the L plus 1. This is equation 7.2.10. Similarly, for the last interior node, I equals m, negative lambda t times m minus 1, tm minus 1 to the L plus 1 plus 1 plus 2 times lambda t to the tm to the L plus 1 is equal to tm to the L plus lambda times function of f m plus 1 to the times t to the L plus 1. This is equation 7.2.11, where fm plus 1 times tl to the L plus 1 describes the specific temperature changes at the right end of the rod, I equals m plus 1. When equation 7.2.8, 7.2.10, and 7.2.11 are written for all the interior nodes, the resulting set of m linear algebraic equations has m unknowns. In addition, the method has the added bonus that the system is tridiagonal. Thus, we can utilize the extremely efficient solution algorithms that are available for tridiagonal systems. Example 2, for the simple implicit solutions of the heat conduction equations. Problem statement: use the simple implicit finite difference approximation to solve the temperature distribution of a long, thin rod with a length of 10 cm and the following values. K prime is equal to 0.49 cal per second centimeter degree Celsius. Delta X is equal to 2 cm and delta T is equal to 0.1 second. At T equals 0, the temperature of the rod is 0 and the boundary conditions are fixed for all times. At T, at T0 is equal to 100 degrees Celsius and the temperature at 10 is equal to 50 degrees Celsius. Note that the rod is aluminum with C is equal to 0.2174 cal per gram degree Celsius and ρ is equal to 2.7 gram per cubic centimeter. Therefore, K is equal to 0.49 over 2.7 times 0.2174. So K is equal to 0.835 square centimeter per second and lambda is equal to K times delta T over delta X squared. So lambda is equal to 0.835 times 0.1 divided by 2 square, which is equal to 0.020875. So this is the rod, 10 centimeter rod. We have the given K and the delta X, which is 2 centimeter. So this is the delta X, 2 centimeter each. And the delta T is equal to 0.1 second. So the boundary condition at the at 0, the temperature is 100 degrees Celsius and at 10 centimeter is 50 degrees Celsius. Using the implicit equation 7.2.8 of the implicit method, a negative lambda T I minus 1 to the L plus 1 plus 1 plus 2 times lambda times T I to the L plus 1 minus lambda T I plus 1 to the L plus 1 is equal to T I to the L. At initial time, T equals 0 based on initial and boundary conditions. Current index L equals 0. So at 0, T0 to the 0 is equal to 100. T10 here is T10 is 0. T20 is 0. T30 is equal to 0 and T40 is equal to 0. while T50 is equal to 50. At T equal to 0.1 second, T01 is still 100. So we will look for the T11, T21, T31, and T41. T51 is equal to 50 degrees Celsius. So to find T11, we equate T11 is equal to Ti to the L plus 1 as shown in the equation 7.2.8. So this one, Ti to the L plus 1. Therefore, L plus 1 is equal to 1, and so L is equal to 0 and I is equal to 1. Substitute to equation 7.2.8, negative 0.020875 T01 plus 1.04175 T11 minus 0.020875 T21 is equal to T10, where T10 is equal to 0 and T01 is equal to 100. So negative 0.020875 times 100 plus 1.04175 T11 minus 0.020875 T21 is equal to 0. So equation 1 is then 1.04175 T11 minus 0.020875 T21 equals 2.0875. To find T21, we equate T21 equals to TL plus I to the L plus 1. Therefore, I plus 1 equals 1, L is equal to 0, and I is equal to 2. So negative 0.020875 T11 plus 1.04175 T21 minus 0.020875 T31 is equal to T20, where T20 is equal to 0. So equation 2 is negative 0.020875 T11 plus 1.04175 T21 minus 0.020875 T31 equals to 0. To find T31, we equate T31 is equal to Ti to the L plus 1. Therefore, L plus 1 is equal to 1. So L is equal to 0. And I is equal to 3. Negative 0.020875 T21 plus 1.04175 T31 minus 0.020875 T41 is equal to T30, where T30 is equal to 0. So equation 3 is negative 0.020875 T21 plus 1.04175 T31 minus 0.020875 T41 is equal to 0. To find T41, we equate T41 equal to Ti to the L plus 1. Therefore, I plus 1 is equal to 1. L would then be equal to 0 and I is equal to 4. So substitute in the equation of implicit method, we have negative 0.020875 T31 plus 1.04175 T41 minus 0.020875 T51 is equal to T40, where T40 is equal to 0. Negative 0.020875 T31 plus 1.04175 T41 minus 0.020875 times 50, where since T51 is equal to 50. So it is multiplied to 50 is equal to 0. Equation 4 would be negative 0.020875 T31 plus 1.04175 T41 equals 1.04375. So this can the four equations can be transformed into the matrix form, where the unknowns are T11, T21, T31, T41. This can which can be solved for the temperature at T is equal to 0.1 second. So now we have T11 is equal to 2.0047, T21 equals 0.0406, T31 equals 0.0209, T41 is equal to 1.0023. We can use this to solve for the temperature at T is equal to 0.2 second. So these are the unknown for the at T is equal to 0.2 second. So T12, T22, T32, and T42 are the unknown. And for the boundary condition, we have T02 is equal to 100 and T52 is equal to 50. By representing the previous process, by repeating the previous process, we have the following equations. 1.04175 T12 minus 0.020875 T22 equals to 4.09215 in equation 1. Equation 2 is negative 0.020875 T12 plus 1.04175 T22 minus 0.020875 T32 equals 0.04059. Equation 3 is negative 0.020875 T22 plus 1.04175 T32 minus 0.020875 T42 is equal to 0.02090. Equation 4 is negative 0.020875 T32 plus 1.04175 T42 equals 2.04069. So we transform these four equations into the matrix form, where the unknown are T12, T22, T32, and T42. The simultaneous equations can be solved for the temperatures at T equals 0.2 seconds. So we have T12 is equal to 3.9305. T22 is equal to 0.1190. T32 is equal to 0.0618 and T42 is equal to 1.9653. Whereas the implicit method described is stable and convergent, it has the defect that the temporal difference approximation is first-order accurate, whereas the spatial difference approximation is second-order accurate in figure 7.8. In the next section, we present an alternative implicit method that remedies the situation. Before proceeding, it should be mentioned that although the simple implicit method is unconditionally stable, there is an accuracy limit to the use of large time steps. Consequently, it is not that much more efficient than the explicit approaches for most time variable problems. Where it does shine is for steady state problems. An alternative approach would be to run a time variable solution until it reached a steady state. In such cases, because inaccurate intermediate results are not an issue, explicit methods allow you to employ larger time steps and hence can generate steady state results in an efficient manner. Next is the Crank-Nicholson method. The Crank-Nicholson method provides an alternative implicit scheme that is second-order accurate and in both space and time. To provide this accuracy, difference approximations are developed at the midpoint of the time increment in figure 9. To do this, the temporal first derivative can be approximated at t to the L plus 1/2 by the derivative of t with respect to time is approximately equal to ti to the L plus 1 minus ti to the L over delta d. This is equation 7.2.12. The second derivative, its base can be determined at the midpoint by averaging the difference approximations at the beginning t to the L and at the end t to the L plus 1 of the time increment. So the second derivative of t over del over the with respect to x is approximately equal to 1/2 times ti plus 1 to the L minus t 2ti to the L plus ti plus 1 to the L over delta x squared plus ti plus 1 to the L plus 1 minus 2 times ti to the L plus 1 plus ti minus 1 to the L plus 1 over delta x squared. Figure 9 shows a computational molecule for the Crank-Nicholson method. So substituting equations 7.2.12 and 7.2.13 into equation 7.2.1 and collecting terms gives negative lambda ti minus 1 to the L plus 1 plus 2 times 1 plus lambda times ti to the L plus 1 minus lambda ti plus 1 to the L plus 1 equals lambda ti minus 1 to the L plus 2 times 1 minus lambda times ti to the L plus lambda ti plus 1 to the L, where lambda is equal to k times delta t over delta x squared. As was the case with the simple implicit approach, boundary conditions of t0 to the L plus 1 equals f0 to the times t to the L plus 1 and tm plus 1 to the L plus 1 equals fm plus 1 times t to the L plus 1 can be prescribed to derive versions of equation 7.2.14 for the first and the last interior nodes. For the first interior node, 2 times I plus lambda times t to t1 L to the L plus 1 minus del lambda times t2 to the L plus 1 equals lambda f0 times t to the L plus 2 times 1 minus lambda t1 to the L plus lambda t2L plus lambda f0 times t to the L plus 1. And for the last interior node, negative lambda tm minus 1 to the L plus 1 plus 2 times 1 plus lambda tm L plus 1 equals lambda f times f m plus 1 times t to the L plus 2 times 1 minus lambda tm to the tml plus lambda tm minus 1 to the L plus lambda fm plus 1 times t to the L plus 1. Although equation 7.2.14 through 7.2.16 are slightly more complicated than equations 7.2.8, 7.2.10, and 7.2.11, they are also tridiagonal and therefore efficient to solve. So same example for the same example on the problem. Use the Crank-Nicholson method to solve the temperature distribution of a long thin rod with a length of 10 cm and the following values. K prime is equal to 0.49 cal per second centimeter degree Celsius. Delta X equals to 2 cm. Delta T is equal to 0.1 second. At T equals 0, the temperatures of the rod is 0 and the boundary conditions are fixed for all times. At T0 equals 100 degrees Celsius and T10 equals 50 degrees Celsius. Note that the rod is aluminum with C equals 0.2174 cal per gram cal per G degrees Celsius equals to rho equals 2.7 G over cm cubed. Therefore, K is equal to 0.49 divided by 2.7 times 0.2174 equals 0.835 square centimeter per second. And lambda equals to 0.835 times 0.1 over 2 square equals 0.020875. For the solution, equations 7.2.14 through 7.2 Point 16 can be employed to generate the following tridiagonal set of equations. So this is the matrix form to find the unknown T11, T21, T31, T41, which can be solved for the temperatures at T equals to 0.1 second. So we have T11 is equal to 2.0450, T21 equals 0.0210, T31 equals 0.0107, and T41 equals 1.0225. To solve for the temperatures at T equals 0.2 second, the right-hand side vector must be changed to 8.1801, 0.0841, and 0.0427, 4.0901. So the simultaneous equations can then be solved for T12 equals 4.0073, T22 equals 0.0826, T32 equals 0.0422, and T42 equals 2.0036. So that would be all for the simple implicit method and the Crank-Nicolson method.